Chapter 6, Conversions and Calculations. So as you can tell, this is a math chapter. So we will go over the examples and we'll go over the whole chapter. So try not to stress out too much. If you've already taken the math mod, then you should be, this should be a review for you. And if you have not, this will kind of help you when you get to the math. So we should cover all of these in the chapter, so I'm just going to skip past them for now. So the ability to manipulate conversions and make calculations is a requirement of pharmacy technicians. Unfortunately, in many cases, when math is mentioned to new pharmacy technicians, it can trigger instant stress by reminding students of previous bad experiences. However, pharmaceutical calculations are performed on a daily basis and applied to the medications prepared in class and at work. The repetitiveness of these conversions and calculations reinforces the student's technician's knowledge and confidence. It is important to learn and feel comfortable with the basic conversions. This chapter will describe the types of calculations used through history, Roman numerals and military time, common math problems, including multiplication, division, fractions, decimals, percentages, and ratios. We will also focus on these areas: allegations, the apothecary system, Avery-Dupont system, dilution. Dimensional analysis we don't cover here, but I'll explain why later. And then dosing and using milligram per kilogram and body surface area, household system, infusion rates, drip rates, and drop factors, and the metric system. Some special calculations for infants, children, and senior citizens are discussed. These patients deserve special consideration because of the metabolic differences that exist before adolescence and in old age. Medication dosing is discussed for the following medications and therapies. So chemotherapy, heparin therapy, insulin, and parenteral nutrition. 4 different measurement systems have been used throughout the history of pharmacy. Most of the systems involve approximate measurements, so the conversion from one system to another is not precise. The pharmacy technician must have a basic understanding of all systems. However, in the United States Pharmacopoeia recognizes the metric system as the official system of measurement for pharmacy. So we only use the metric system in the pharmacy. That doesn't mean the doctors aren't going to write household or apothecary on prescriptions, but we only use metric system. The metric system is based on multiples of 10 and is the most precise of all systems. Technicians in the United States mostly encounter prescriptions expressed in either metric or household systems. For example, most people are familiar with the household measurement of a teaspoon. When writing prescriptions, many prescribers prefer to use 5 milliliters in the metric system rather than 1 teaspoonful. These two measurements, one in the household system and one in the metric system, are considered to be equivalent. The pharmacy technician must translate the physician's orders into terms an average person can understand. Always reread what will be printed on the prescription label to consider whether it will make sense to the layperson. Never assume that a person understands the meaning of a measurement. This precaution reduces the chance of any misinterpretation of the instructions. So I always tell people, when you're typing in a prescription, before you hit submit or enter to send it off to the pharmacist or whatever, you should reread your directions, proofread them, make sure they sound good. Because sometimes you'll be typing so fast you don't realize that you made a typo or you didn't translate something properly. So although Arabic numerals, which are just our regular numbers, 1, 2, 3, 4, 5, and so on, are commonly used in the United States, physicians do not always use this system when ordering medications. Instead, they may use Roman numerals to indicate the quantity of tablets or capsules, the number of fluid ounces, or the number of refills. Roman numerals may be either uppercase or lowercase letters. When using Roman numerals, begin with 1, 2, and 3, then write IV, 1 less than 5 to equal 4. Repeat the process at 9 by writing IX to equal 9. To write 40, write XL. However, to write 49, use XLIX. An important one is the fraction 1/2 is written as lowercase ss with a line over both letters. Table 6.1 gives you a nice little chart for Roman numerals. It's good for studying. And then we have the rules for determining Roman numerals. So first the numbers are represented by combinations of the letters I, V, X, L, C, D, and M, which represent 1, 5, 10, 50, 100, 500, and 1,000 respectively. When a numeral is repeated, its value is repeated. A numeral may not be repeated more than 3 times. V, L, and D are never repeated. And when a smaller numeral is placed after a larger numeral, it is added to the larger numeral. And when a smaller numeral is placed before a larger numeral, it is subtracted from the larger numeral. V, L, and D are never subtracted. LC is correct. Never subtract more than 1 numeral. When subtracting, only subtract powers of 10. Only use a numeral before the next 2 higher value numerals. And use I before V and XX before L and C and C before D and M. So if that's not confusing at all, you kind of know what you're doing. The rules to me are a little confusing reading them out. Looking at the chart though, and then looking at the rules, I can kind of see what they're talking about. But if you don't know your Roman numerals very well, it's going to be hard to look at these directions at first. So when working with Roman numerals, remember that if a large number is placed in front of a smaller one, you must add the 2 to determine the value. So you can see that here, they have put in the 10 and the 5, and then it equals 15. So you can go through exercise 6.1 and change all of these to Arabic numbers. That's a good practice. I highly suggest it. And let's just scroll back up to the top and see if any of these happen to be in our chart. So let's see if IX is here. It is. So IX down there. So this would be not. So you can look at the chart up there and kind of just practice. In a hospital or institutional setting, international time, also known as military time, is used exclusively. Orders are written 24 hours a day, and a system is needed to ensure that all medical related caretakers understand exactly when an order was written and when the medication or treatment is to take place. The system is based on 100, starting at 100 hours midnight and continuing with 100 hours 1 a.m. The clock runs through to 2300 hours, which is 11 p.m. and restarts again at midnight, which is 0000. This system is easy for most people to use through noon, but then it can become confusing as the clock hands begin to make their second trip around the face of the clock in the PM hours. The numbers continue. For example, so 1200 is noon, so 1300 is 1, 1400 is 2, 1500 is 3, and so on and so forth, up back until midnight. Minutes are added to the hours in the last 2 places through 59. For instance, 1:32 p.m. is 1332 and 12:01 a.m. is 0001. When the pharmacy receives orders, the receiver must check the date and time against previous orders to ensure that the most recent order is in effect. Using this system, there's never any question as to when an order was written or which order supersedes another. So then you got a little chart here to help you study. And then you have some quick practices you can go through. All right. So temperature conversions between Fahrenheit and Celsius. The Fahrenheit temperature scale is most commonly used in the United States. Freezing is 32 degrees Fahrenheit and boiling is 212 degrees Fahrenheit. The Celsius scale is used in countries that regularly use the metric system. The metric system is based on multiples of 10, and the Celsius temperature scale goes from 0 degrees Celsius as the freezing point to 100 degrees Celsius as the boiling point. It is sometimes necessary to convert between these two scales. Formulas for converting can be written with fractions or decimals as follows. So here is the formula from going from Fahrenheit to Celsius and Celsius to Fahrenheit. So now we will do an example problem. Okay, so we're going to be going from Fahrenheit to Celsius and Celsius to Fahrenheit. You can see the two different formulas that I mentioned before. I'm going to use the decimal equation for both of them. So for the first one, we're going to convert from 98.6 degrees Fahrenheit to Celsius. We're going from Fahrenheit to Celsius. So the formula we're going to use is the C equals F minus 32 over 1 point. All right, and then we're going to go from 98.6 degrees Fahrenheit, and we want to go to Celsius. So now I'm just going to rewrite the equation with 98.6 plugged in for the F, because that is our temperature in Fahrenheit. So then I'm just going to rewrite it. And so in your calculator, you need to first take care of the top. In the book, you can see that there is parentheses. We always take care of parentheses first. So what I'm going to do first is do 98.6 minus 32. And I get 66.6. So now I'm going to rewrite that again. 60, this time getting rid of the top part and just filling in my answer. And then keeping my 1.8. So now I'm just going to do 66.6 divided by 1.8. And I get the answer of 37 degrees Celsius, which is the answer. All right. Now we're going to go from Celsius to Fahrenheit, and we're going to convert 100 degrees Celsius to Fahrenheit. So I'm going to rewrite that, the equation for this one. So C to F. F equals 1.8. Okay, so we're gonna do 100 degrees Fahrenheit. So now I'm just gonna rewrite it, plugging in. Sorry, we're going from 100 degrees Celsius. I didn't mean to say that. Oh my gosh, I just did it again. So 1.8 times 100 plus 32. So 1.8 times 100 plus 32 gives us 212 degrees Fahrenheit, which is the answer. It is important for pharmacy technician students to review and be comfortable with basic math skills, such as adding, subtracting, multiplying, and dividing whole numbers, fractions, and decimals before adding new skills. Multiplication is used repeatedly in pharmacy calculations. Sometimes it is necessary to increase or reduce a prescription. Multiplication by a number greater than 1 is used to increase the formula, and division, which is the same as multiplying by a proper fraction, is used to determine a part or portion of a prescription. So I always tell the students, if you're not good with your multiplication chart, it's probably going to be really hard for you to think of multiples and the least common denominator when it comes to when we do fractions. And obviously, any other time you're going to have a calculator. So I think it's really important that you know all of these, but if you're not good at them, I suggest just kind of practicing through them. It's going to make your life a lot easier in the math mod. And for some of these problems, we might do this. A fraction consists of a numerator and denominator. The numerator is the top number in the fraction, and the denominator is the bottom number. The numerator of a fraction shows the number of equivalent parts in the whole, and the denominator shows how many are being considered as the whole. If an object is divided into 4 parts, one part can be expressed as 1/4, or 1/1 of the whole 4. So if we have a 1,000 milligram tablet, we split that in half. A half a tablet is 500 milligrams, and 1/4 of a tablet is 250 milligrams. So if there's 1/4 of that is 250. So 250 times 4 is 1,000, and 500 times 2 is 1,000. We'll go over those. We'll go over fractions more in just a second. So there are 3 types of fractions, proper fractions. The numerator is smaller than the denominator, so the top number is smaller than the bottom number, and the value is always less than 1. So you can see an example here. 1/2 is a proper fraction. Improper fraction, the numerator, so the top number is greater than or equal to the denominator, and the value is always greater than or equal to 1. So we have this one, for example, 5/2. That is an improper fraction. A whole number and a proper fraction combined is a mixed fraction. So 5 1/2. And we will Now go over some of these. Okay, now we're gonna go over some fractions. So just a little reminder. This right here, the first one is a proper fraction. Then we have an improper fraction, which the numerator is greater than or equal to the denominator. Then we have a mixed number, a whole number, and a proper fraction combined. Okay, so number one here says converting a proper fraction to a decimal. So we are going to divide the numerator by the denominator. So they already did 1/2 in the example, which is 0.5. So what they did was they just did 1 divided by 2, and that's how they got 0.5. Let's do the 3/4. So all you would do is take the top number and divide it by the bottom number. And we get 0.75. Okay, so let's do an improper fraction. So number 10 on the quick check. Same thing, 9 divided by 5 is 1.8. So let me just write that here. So 9 over 5 is 1.8. 1/2 was 0.5, and 3/4 was 0.75. Okay, so now we're going to convert a mixed fraction to a decimal. So the book first says that 3.5 equals 3 plus 1 divided by 2. So just taking that fraction and doing 1 divided by 2, which equals the 3 and then 0.5. So if you can do that and remember to not forget to add in that whole number, which a lot of people do when they do the mixed fractions to decimals this way, you are more than welcome to do whatever way gets you the correct answer. If you know a different way, by all means do that. What I like to do is convert to an improper fraction first. So let's do number 6, which is 1 1/8. So to change a mixed number to a improper fraction, first thing we're going to do is do 1, take that 8 and that 1 and multiply them together. So 8 times 1. And then we're going to add the numerator. So plus 1. So now I have 9, which is now going to be my top number, and my 8 will stay. So now if I want to find out the decimal version, I would do 9 divided by 8, and I get 1.125. The term percent and its corresponding sign means per 100. Percentages represent a portion of a whole. The number 100 is used to represent the whole, therefore 1000 equals the whole. And that is going to be very important for you to remember for pharmacy. And we will go over some of these problems. Okay, so now we're going to do some percentages examples. We're going to first convert from a decimal to a percentage. So you can see here in this example, 0.75, that's the decimal. We want to convert it to a percent. To convert it to a percent, we're just going to multiply it by 100 because percentages are always out of 100. And we get 75%. So if we had 0.65, we would multiply that by 100. And we would get 65%. So that's how you do those. So to convert a fraction to a percentage, first we need to turn it into a decimal. So just like we did in the other example before this percentage, we're just going to take the fraction. So they have 1/2, which is 50%, which most of you probably know that. Let's do 2/3. So first we need to turn it into a decimal. So we're going to go 2 divided by 3, which gives us 0.67, we'll say, for rounding, which we'll talk about next. And then we are just going to multiply that by 100. So first you need to take your fraction and turn it into a decimal, just like we were doing up here. And then you get the percentage by multiplying by 100. Okay, so rounding a number. First, we're going to determine to what whole number or decimal place the number is to be rounded. So the assignments, if they want you to round to a certain decimal place, they will tell you. Look at the number to the right of the value being rounded. If that number is 5 or greater, round up, or if it's less than 5, round down. So for instance, here in this first example, we have round to a whole number. So they had the number 3.4. So using these rules, they wanted it just to be a whole number. So next to the 3 is a 4. So we would round down. So that would be 3. In here, round to tenths place. So we want to have just one number after the decimal. And we have the number 3.45. So because there is a 5 here in this spot, in the hundredths place, we are going to round this 3.4 up to 3.5, and then we have the answer rounded to tenths, and so on and so forth. All right, now we can convert percentages to decimals. So to convert a percentage to a decimal, drop the percent sign and divide by 100. So they have 60%, they dropped the percentage sign, and it was just 60 divided by 100. And why is it out of 100? Because percentages are always out of 100. So let's do 45%. We will just take it and do 45 over 100. which gives me 0.45. Now, from converting percentages to fractions, we're gonna convert a percentage to a fraction by dropping the percent sign, placing the number over 100, and reducing. So here they have 60%. They put this. All right, so now we're going to convert decimals to fractions. To convert a decimal to a fraction, place the decimal over 1. Then, as in the previous example, you must multiply the top and the bottom of the fraction by a multiple of 10 to remove the decimal point because decimals cannot be part of a fraction. So, you can see that example there, 0.02. Let's do another one. Let's do 0.05. So it wants you to multiply or take that number. So So 0.05 and write that over 1. And then we need to multiply each one of these by 10n. And n is equal to the number of decimal places, the number of digits after the decimal place. So for here we have 2. So that would be 10 to the 2, which is really 10 times 10, which is 100. So like they said, 100. And you can do that way. But say if there's only one number here, you could just do multiply by 10 and then you wouldn't have to reduce. If that's confusing, just don't listen to me right now. You'll learn more about it later. So now we have 100. 100 times 1 is 100. And then 100 times 0.05 is 5 over 100. And that is not two lowest terms. So I'm going to divide each one by 5 because I know I'll get a 1 on top and that will be lowest. So 5 divided by 5 is 1. And 100 divided by 5 is 20. A ratio expresses a relationship between two quantities or measurements. The following expression is written as a ratio, 1 to 2, which is read 1 is to 2. A ratio can also be written as a fraction in which the first number is the numerator and the second number is the denominator. This ratio can be written either as 1/2 or as 1 to 2. When technicians compound products, they may be required to solve problems using ratios, which can be considered parts or fractions. So we'll go over an example. To convert ratios to percentages, first express the ratio as a fraction, then convert it to a decimal, and finally multiply the decimal by 100 and add the percentage sign. So they have 3/4. So really ratios are the same thing as fractions. They are the same thing. So 3 to 4 is the same as 3 over 4. So let's do another one. So I have 3 over 4. Let's do 2 over 5. So first we need to turn that into a decimal. So remember for decimals, we're going to do the top number divided by the bottom number. A proportion is an equivalent relationship between two ratios, and proportions are going to be like the number one math we do in pharmacy. So you can see here, this is a proportion saying 1/2 is equal to 2/4. And then here's it in ratio. And we will go over some examples of these. All right, so we're gonna do proportions. So proportions in the healthcare industry is the majority of the math that is done. For us, it's like 75% of the math that we will do in our career. And in this program, quite a bit. So proportions are, they can be solved in two ways. The first involves cross multiplying and dividing. The second method is described as means and extremes. We are not going to do means and extremes. We are going to do cross multiply and divide. So for here, you see that they have 7x because we cross multiply diagonally. So you can do 7x equals, and then write the 3 times the 21 if that's easiest for you. And I do think that way is pretty simple. I tend to skip doing the x and doing it the other way, but it's the same thing. So let's say we have 3/7 is equal to x over 21. So then it's like 7x equals 3 times 21. So then we would just do 3 times 21 is 63. And then we'll write 7x here. We want to get x alone, so we need to divide each side by 7. X is now by itself. And 63 divided by 7 is 9. And that is the answer. So, oops, x equals 9. Now, the way that I was taught to do it, it's literally the same way, but a little different. So I'll just do that for you right now, just so you can see. You might have learned this way as well. So the way I learned it is never touching the x in your math problem and while you're doing it. So we're going to cross multiply the two numbers that are diagonally from each other. So we couldn't do 7. So like on this one, we did 7x. This other method, we couldn't cross multiply the 7 and the x because we wouldn't get an answer. So first we are going to cross multiply that 3 by the 21, like just kind of how we did in the other method. That's 63. We're going to divide by what's left, which is 7. We've used all 3 of those numbers, and of course we get the answer of 9. So whatever way is easiest for you to get that answer. And we will practice this quite a bit more as we go along. Many pharmacy technicians have difficulty interpreting word problems. One way you can lessen the confusion of a word problem is by identifying what is known and what is being asked. One of the first things to remember is to dismiss unnecessary information, which you will see. In the following ratio and proportion examples, identify what strength you have in stock and what strength you need. Next, set up the equation and double check the calculations. It is important to remember to place the correct units in the correct positions. And we will go over that in just a second. So working with word problems, I always hear from students that word problems are the most difficult for them. And can't we just do problems? Well, the problem with that is in the real world, you are not going to just be given a set of math problems on the job to do. You're going to be figuring out real time patient's dosaging information and dosage calculations. So if we didn't give you word problems, you wouldn't learn how to do it. So for word problems, we're mostly going to use proportions. As we go along further into math and the math mod, we will use several different ways to solve. Like there might be one or two different answers in a problem. So let's do example 6.4, a single step ratio and percentage problem. So you receive an order for Ativan 4 milligrams. You have 2 milligrams in stock. How many 2 milligram tablets will you need to fill this order? So they have 2 milligram over 1 tab equals 4 milligram over X. So with proportions, when it comes to units, you're going to make sure that they are always the same rate directly across from each other. So they did 2 milligrams as 1 tab. If I wanted to write the 1 tab on top and then 2 milligram on bottom, that would be totally fine. I would get the right answer as long as I made sure I matched up the units across. So, and that's going to be important when we get into a little more difficult. So if I have milligrams here, I have to have milligrams here. If I have tabs here, I have to have tabs here. It's asking me how many 2 milligram tablets do I need to fill 4 milligram order. So my 4 milligram is going to go here, and I don't know how many tabs, so that is going to be my X. So you could do 2X equals 4 times 1. 4 times 1 is 4. 2X equals 4. We want to get X alone, so we got to get rid of that 2. We have to do the same on the other side. So 4 divided by 2 is 2, and the answer is 2 tabs. For a measurement to make sense, it must have a number and a unit. Different measurement systems use different units. For example, the household system uses teaspoons and tablespoons for small volumes, whereas the metric system uses milliliters for this size measurement. All answers must have a unit or they are incorrect. Ordering 2 per day makes no sense because it could mean 2 tablets, capsules, teaspoons, milligrams, grams, milliliters, and so on. The USP recognizes the International System of Units or metric system as the official system of measurement for pharmacy in the United States. The metric system can be used to measure weight, volume, and distance. The basic unit of the measurement for weight is the gram. For volume, it is liters, and for length, it is meters. A pharmacy technician will use the prefixes micro, milli, and kilo along with the base unit. So here in table 6.3, we have the metric prefixes and their meanings. In the metric system, each unit of measurement is a multiple of 10. So to convert from a larger unit of measurement to a smaller unit of measurement, multiply by a multiple of 10. And to convert from a smaller unit of measurement to a larger unit of measurement, divide by a multiple of 10. And we'll show you how to convert to where it's not confusing doing it this way. Okay, we'll do some examples of that. All right, so metric measurements. These 3 here are conversion factors. just want to go back down here. So the book has converting between units with dimensional analysis. So we do not teach dimensional analysis at Ross. I think it's super confusing for students. Some students learn that way though. So if you did, and that's the easiest, most comfortable way for you to do any of this math, then by all means, go ahead. So a conversion factor is a fraction equal to 1, which is used to change the unit of measurement, but not the value. So we have these following conversion factors that we use in the metric system. 1,000 micrograms is equal to 1 milligram. 1,000 milligrams is equal to 1 gram. 1,000 grams is equal to 1 kilogram, and 1,000 milliliters is equal to 1 liter. So 5 grams equals how many milligrams? So essentially the same way they do it. So they have the conversion factor of 1 gram equals 1,000 milligrams. Okay, so 1 gram is equal to 1,000 milligrams. And we want to convert, what was it, 5 grams? Yes. So just like I said before, you can do this in a proportion. So we have to have the same units across, directly across. So grams and milligrams. Where we have 5 grams, we want to know how many milligrams this is. So essentially that's what this fraction is. This over here is what we know. 1 gram is equal to 1,000 milligrams, that we know. This side we don't know. All we know is we have 5 grams and we want to find out how many milligrams that is. So when you're setting up these problems, that is what you will do, especially as we progress into the, like when we're in the math mod. And those of you that have been in the math mod know what I'm talking about. Anyway, so we would just do the same thing. We're going to cross multiply the two numbers that are diagonally from each other. This is the method that I use. I'll do the other method in just a second. So 5 times 1,000 and divide that by 1, which is what I have left, which is 5,000. So you can see it, 1 gram is 1,000 milligrams. So 5 grams has to be 5,000 milligrams, right? Because if 1 gram is 1,000, 2 grams is 2,000, 3 grams is 3,000, 4 grams is 4,000. So if you can kind of train your mind to think like that, you might not even have to do these in your head at some point.
One of the incidents also spread fast among the other bartenders via a group text.
So there was a couple of people in the group chat that said, hey, you need to go to the police.
So 250 micrograms equals how many milligrams? So we have that conversion factor of 1 milligram is 1,000 micrograms.
She and Ryan didn't know anything about Bianca's death. I'm like, I don't think you should do anything about that. So they let it go. Weeks went by. The Lori bar blow up seemed to fade away. Until
One of the bartenders sent a link.
So now we can do the other way, which is just doing the metric system can also be converted into household liquid measurements. The main dry weight measurement in the system are pounds and ounces. Table 6.4 shows the household measurements of volume, their abbreviation, and their equivalent. 6.5 shows household volumes and metric volumes. And we will go over how to convert some of those.
At last.
Okay, household measurements. So we're going to convert between the two, just like we did in the other ones. So using conversion factors, which is all of these here and more.
Cabo San Lucas was a special place for Larry Rudolph and Lori Milliron. They visited often, brought Lori's kids.
So how many milliliters are in 2 tablespoons? Use 1 tablespoon equals 15 ml.
According to a term, John did.
The flying down there, Christmas holidays. Like landed, Lori seats, next to place, lining up on the tarmac. They came in, they started asking people's passports.
So we have to have the same units across again. And we want to know how many milliliters. So X milliliters are in 2 tablespoons. So if we do 1X for the 1 tablespoon to X is equal to 2 times 15.
To one of those insurance companies. He spoke with Lori by phone from jail. The recordings have never been.
We want to get X alone, so we want to divide that by 1. Which gives us 30 M.
That is.
Okay, so now we'll do some examples from the apothecary system.
Happened all the way.
So just a little note on some of the symbols. So we have GR. That is grains, not grams. I'm gonna put that here because so many people get that confused. Grams is G. Sometimes they'll say GM in different places, but GR is grains. Then we have an M for minims. We have the symbol for dram. We have the symbol for ounce, which is like the dram symbol with like kind of a Z on top. And if it's fluid, you would just put an FL in front of it. So that's just a little overview on the symbols.
What the typical scale. So Dr. Deducted it one more time. It's right here.
All right, so we are going to convert how many grains are in 325 milligrams of aspirin. Use 1 grain equals 65 milligrams. And you can see here that the grains is written first because in the apothecary system, we put the units before the number and the numbers are in Roman numerals. So if we use 1 grain equals 65 milligrams, we need to have milligrams here and grains here. The aspirin is 325 milligrams. We want to know how many grains. So if we do 65x equals 1 times 3, 25. We do the multiplication first. We get 325 over here. We want to get x alone. So to do that, we need to divide by 65 here, and then also divide by 65 here. Which gives us 5 grains, which in the apothecary system, we would write as GR for the symbol first, and then V for 5. So that would be your answer. The Ava-Dupias system is another type of measurement that originated in England. The Ava-Dupias system is the most common system of commerce. It is through this system that items are purchased and sold by the ounce and pound. The Ava-Dupias system is similar to the apothecary system because it also uses grains, ounces, and pounds for weight. So we have the Ava-Dupias weight, the dry weights and liquids, and metric equivalents. Dry weights use grains, ounces, and pounds. Liquid volumes are fluid ounces, pints, and gallons. And we will go over some examples. So for the Ava-Dupias system, it's another type of measurement that originated in England. It's very close to the metric system, same type of rules. Converting is going to be the same way. We have this sheet here with conversions, or this table here with conversions.
Gave them some suspicion, and her will showed that she in fact wanted to be cremated.
And then we have some practice problems that you can do here.
2016, 6 months before.
You should know how metric system units compare to other units of measure, such as ounces and grains. Most of the time they convert easily, but sometimes there are variances, making conversions between measurement systems approximate in these instances. Because the metric system is the approved system of measurement used in pharmacy, it is the measurement system you should use when preparing a compounded drug. However, you will see differences among manufacturers' products and their weights. For example, some manufacturers consider 473 ml to equal 1 pint, whereas others consider 480 ml to equal 1 pint. The rule is to follow the metric system because it is the approved system of measurement for pharmacy in the United States. So here's some dosing schedules. BID, these are SIG codes, equals 2 times daily every 12 hours. Or Q12H every 12 hours. TID means 3 times a day. QAH means every 8 hours. QID means 4 times daily. And Q6H means every 6 hours. All right, now we'll do some examples of calculations with liquid medication. Okay, so calculations with liquid medication. These are single step problems with liquid medications that can be solved by ratio and proportion. So we have an order for Docusate 20 milligrams BID. So we need to give the patient 20 milligrams, but in stock, we only have Docusate sodium in 4 milligrams per ml. So how many milliliters are needed per dose? So we're gonna do a proportion. And on one side of the proportion, we're gonna put the strength of the medication. Which was 4 milligrams per ml. And remember, we have to have the same units directly across, so milligrams should be here, milliliters should be here. We're trying to find out how many milliliters to give them for 20 milligrams. So we could write this as 4x is equal to 20 times 1. Or you can solve it the way with not touching the x, which is usually the way I solve it in class. But for this, I like to kind of teach it this way since the book does. So 20 times 1 is 20. And then we have 4x. We want to get x alone, so we're going to divide both sides by 4. And we get that x is equal to 5. Which is what they got, 5 ml. So in order to give the patient 20 milligrams, we have to draw up 5 mLs of the medication that we have in stock, which is 4 milligrams per ml. All official compounding drug references and drug manufacturers provide proper dosing regimens. When these are based on kilograms and the patient's weight is provided in pounds, it is necessary to convert pounds into kilograms. It is important to remember that there are 2.2 pounds per kilogram. And that's a huge one to remember. And we'll do a example. Okay, so calculating the proper dose using body weight. So we have this conversion factor of 1 kilogram is equal to 2.2 pounds. And that is going to be one that you want to remember off the top of your head, especially if you work in hospital, because you're going to be using it a lot. So what is the weight in kilograms of a 176-pound person? So we are going to do a proportion. So on one side of the proportion, I'm going to do the 1 kilogram is equal to 2.2 pounds. And again, I could put this on this side if I wanted to. It really doesn't matter. They're equal to each other, so it can be on either side. And if I wanted to put the 2.2 pounds on top and the 1 kilogram on the bottom, I technically could, as long as my units matched directly across, I would get the same answer. So the person weighs 176 pounds and we want to find out how many kilogram they are. So we're going to do 2.2x is equal to 1 times 176. So 1 times 176 is 176. And then we will just rewrite this. We want to get x alone, so we need to get rid of that 2.2 by dividing by it. Now we have x alone. And then, of course, we have to do that on the other side. So 176 divided by 2.2 is 80. So the patient weighs 80 kilograms. So the one we just did was a single step body weight problem. this example involves 2 steps. And we're not gonna do it this way like they show in the book, dimensional analysis. Um, but again, if that works for you, great. You can definitely do it if you're getting the right answers. So the dose ordered is 2.5 milligrams per kilogram per dose, and they want the dose every 8 hours. The patient weighs 250 pounds. How many milligrams per dose? So first we need to find out how many kilograms they weigh. So again, we'll do a problem just like we have up here. 1 kilogram, 2.2 pounds is equal to 250 pounds x kilogram. So we would do 2.2x is equal to 250 times 1, which is 250. We need to get rid of that x. I'm sorry, I want to get x alone. So we want to divide both sides by 2.2. And then we have our x alone, and then we're going to divide this by 2.2. So 250 divided by 2.2 means that they weigh 113.6, we'll say, kilograms. And the medication should be dosed at 2.5 milligrams per kilogram per dose. So now I'm going to do 2.5 milligrams per kilogram on one side of a proportion. And then on the other side, I will plug in my 113.6 kilograms that I got from the previous problem. And then this would be my x. So this would be 1x is equal to 2.5 times 113.6. Which gives me 284 milligrams, because this is supposed to be milligrams. And we want to get x alone, so we'll divide both sides by 1. 284 divided by 1 is just 284 milligrams. So that's how much they need per dose. So every 8 hours, QAH, they're going to get 284 milligrams. The BSA method of calculating a patient's dose results in the most accurate dose because it is based on both the height and the weight of the patient. BSA calculations are extremely important when determining chemotherapeutic and pediatric doses. A nomogram is a table used to determine the patient's BSA in meters squared. Most hospitals use computer-based programs to determine BSA. And we'll do an example. All right, so calculating body surface area. So it says solve BSA calculations in the same way you would a dosing problem based on weight. And again, they have this example here in dimensional analysis, which we will not use. But again, if you can get the right answer and that makes sense to you, great. We're actually going to do the first one on the quick check 6.13. So the patient is 60 inches, that's their length. Their weight is 85 kilograms and their BSA is 1.8 meters square. The dose is 200 milligrams per meter square. So meters square is the BSA. A lot of students will get like scared by that because I think they need to do something with the 2. You don't. You're just paying attention to that number. And that number is based off of the height and weight of the person. And it's done on a nomogram sheet, which they do not, for some reason, have in this book, I don't think. But we will revisit that in the math mod, or if you've been in the math mod, you should have practiced using a nomogram. Okay, so move down here. So the question is, how many milligrams are required per dose? So I'm going to look at this dose here of 200 milligrams per metered square. And I'm going to put that on one side of a proportion. Oops. Oh, I two did that. All right, and then remember that the patient's BSA was 1.8 metered square. And again, we have to have our units matched directly across. So we would do 1x is equal to 200 times 1.8. 200 times 1.8 is equal to 360. And then we have a 1 over here, so we know it's going to be 360, but to get the x alone, we need to divide both by 1, which is just going to be 360. So that is how many milligrams they need based off of their body surface area. When filling oral prescription orders for pediatric patients and those who cannot take solid dosage forms, you may need to provide an oral syringe with the prescription. A needle cannot be attached to an oral syringe, which reduces the possibility of administration errors. In the case of injectable medications, every possible syringe size can be selected to withdraw the correct volume of solution. So we have a little medicine cup, we have a medication dropper, and we have a syringe. Liquid medications are used frequently for children and elderly patients. It is important that the parent understand how much medicine to give a child using pharmacy supplied measuring devices, usually marked in household and metric measurements. Increases the accuracy of dosing. Very small amounts may be measured with droppers. The pharmacist, not the technician, should show the parent of a patient how to measure the correct amount. Senior citizens must also be careful to take the correct amount of medication. For oral liquids, dosing devices with large boldface calibrations may help the geriatric patient see the medication correctly and give the correct amount. And many of these types of dosing devices are sold over the counter. So pediatrics refers to the practice of medicine in children from childbirth into adolescence, and this range of age is subdivided into various groups. So neonates are from birth to 1 month. An infant is 1 month to 1 year. Early childhood is considered 1 year through 5 years. Late childhood is 6 years through 12 years, and adolescence is 13 years through 17 years. All right, we'll do an example. Two other methods can be used to calculate pediatric doses. Clark's rule uses the child's weight in pounds divided by 150 pounds, the average weight in an adult, as the basis for calculating the dose from the adult recommended dose. Young's rule uses the child's age in years divided by the child's age in years plus 12 as the basis for calculating the child's dose from the adult recommended dose. Both of these methods are approximations. So these are not used very often anymore. So some other methods of calculating pediatric doses are using the Clark's rule, Young's rule, and there's one more that's not in this book, but one more that we'll use. There is no examples of this, but in a problem, it would give you the weight of the child in pounds or kilograms. Then you would divide that by 150 milligrams times the adult dose. So the adult dose would have to be in the problem as well, and that would give you the child's dose. So you have to have their weight in pounds in adult dose to be able to do this problem. I remember the one that's not in here, Freed's rule, which is for infants. We might get to that still in this chapter, if not in the math mod. Young's rule, to do this calculation, you would have to have the child's age in years, and you would have to have the adult dose. So you would plug in the child's age in years here. You would put the child's age in years plus 12. So if they were like 4, 12 plus 4, you would put that number here, what is 16? And then you would multiply that by the adult dose. So the child's age in years, divide that, and that would be the child's dose. Geriatric medicine encompasses the management of illness or disability in the elderly. A major consideration in the dosing of elderly patients is reduced kidney function, which may result in reduced drug elimination or increased drug accumulation, leading to toxic drug levels and adverse effects. Renal clearance is extremely important when using specific drugs in elderly patients. The ISMP has identified certain medications that require additional checks due to a heightened risk to patients if an error occurs. The ISMP has identified certain medications that require additional checks due to a heightened risk to patients if an error occurs. Two of the medications are heparin and insulin, and there should be special safeguards in place to avoid errors with these medications. For a complete listing, you can go to the website listed below. Certain parenteral medications such as insulin, heparin, and penicillin are measured in units per milliliter. Units are assigned to medications called biologicals, which have been tested for potency in biological systems. To prevent errors, healthcare workers should write out the word units rather than abbreviate it as U. And that one's really important because that U can be misconstrued as so many different things. And we can give the patient the wrong dose. Units are specific to each particular medication because the medication has been tested and shown to produce a specific effect relating to the number of units. Therefore, units of heparin have no relationship to units of insulin. So keep that in mind. Heparin is an anticoagulant that is available in many different strengths. Be very careful when using heparin orders and labels because it is considered a high-risk medication. It is available in 100 or 1,000 units per ml, 2,000 units per ml, 2,500 units per ml, 5,000 units per ml, 10,000 units per ml, and 20,000 units per ml. Heparin is also available in 1 unit per ml, 10 units per ml, and 100 units per ml, which are considered heparin Flocklush is used to keep a vein open to prevent clotting so that the line remains open for the next dose. Insulin, a parenteral hypoglycemic medication for lowering the blood glucose level, is also dosed in units. The most common strength used in the United States is U100, which is 100 units per ml. Regular insulin is the only insulin that can be given intravenously. Other types of insulin, in addition to regular insulin, are given subcutaneously. Some insulin comes in U500 strength, which is used only for patients with extreme insulin resistance. Right, so we will work through some of those some of these examples. All right, so calculations involving units and milliequivalents. So we have an example here. We have 2,000, we have two labels here for heparin sodium. This one here says heparin sodium injection USP, 1,000 USP units per ml. So that means every ml the patient receives, they are getting 1,000 units of heparin. This can be given IV or SC use, so IV intravenously, SC subcutaneously. Excuse me. It says here not for lock flush, so this is not for flushing out lines. And then this one here, the only difference is we have 10,000 units per ml. So look at how similar they look. I mean, this is orange and this is more of a brown, but they look almost identical. So these are the kind of things you need to like pay attention and look at, because there's a lot of medications that are like that. And think about the difference between 10,000 units and 1,000 units. Okay, so we have this order for heparin sodium, 4,000 units subcutaneously. In stock, we have heparin sodium, 1,000 units per ml and 10,000 units per ml. How many of each stock volume would we need for the dose? Okay, so we have 1,000 units per 1 ml on one of the labels, and the other one was 10,000 units per ml. And on both of these, on the other side, we know we need to have the same units directly across. So units on top, milliliters on bottom. And we need to provide the patient with 4,000 units. So we want to know how many ml that will be. So let's do the first one. So this would be 1,000, because we go directly across. 1,000 x is equal to 4,000 times 1. 4,000 times 1 is 4,000. And if we want to get the x alone, we have to get rid of this 1,000. So we're going to divide those, and then we'll get x alone, and we have to do the same thing to the other side. So 4,000 divided by 1,000 means we would have to give them 4 ml. So for this problem, 4 ml. Now for this one down here, we have 10,000 units. Oops, I did not mean to write like that. Change the color. So we have x, 10,000 x, and then we have is equal to 4,000 times 1. So again, just like in the previous one, 4,000 times 1 is 4,000. And we want to get the x alone, so we need to divide this side by 10,000 x. So 10,000 crosses off, we just have x left. And then, of course, we have to do it on this side as well. So in our calculator, we're going to do 4,000 divided by 10,000 this time, which is going to be 0.4 ml. So if we were going to give them the 1,000 unit strength, we would have to dose up in a syringe or put into an IV bag, whatever we were doing, 4 ml. And then for the 10,000, we would have to do 0.4 ml. And it says choose the 10,000 unit per ml stock solution in this case to keep the dose volume smaller. So we would use the 0.4 ml, which is more appropriate for a subcutaneous injection, which they like that to be under 1 ml. Okay, so this one's insulin. So remember that insulin is 100 units per ml. That's the strength. That's the strength of like 95% of them. There's a couple other that are different, 200 and 500, but for now, just remember 100 units per ml, and the doctor has ordered 35 units. What volume is needed for this dose? So the doctor wants us to give them 35 units. The strength, oops. The strength is 100 units per ml. And we want to give the patient 35 units. How many ml is that going to be? So this would be 100x is equal to 35 times 1. 35 times 1 is 35. And we want to divide this side by 100, so we get x alone. We also have to do that to the other side if we do it on one side. So we'll have 35 divided by 100, which gives you 0.35 milliliters. Milliequivalents are a type of unit used in the United States to express the concentration of electrolytes such as sodium, potassium, magnesium, and calcium. With liquid medication, these strengths are expressed as MEQ per ml. Make sure to note that the E in milliequivalent is capitalized. With solid medications, the strength can be MEQ tablet or MEQ capsule. Right, and then we'll go through some examples of these problems. Okay, so now calculations with milliequivalents. We're going to follow the same rules. So we have an order for 30 milliequivalents of potassium chloride, KCl, to 1 liter of normal saline. In stock, we have 2 milliequivalents per ml, meaning every milliliter the patient receives, they are getting 2 milliequivalents of potassium chloride. How many milliliters should be added to the NSIV? All right, so let's figure that out. Well, the answer's there, but we're gonna do the example. So the medication strength is 2 milliequivalents per 1 ml. And we want to give the patient 30 milliequivalents. So remember, units are going to go directly across. And this would be 2x is equal to 30 times 1. 30 times 1 is 30, so 2x is equal to 30. We want to get x alone, so if we divide this by 2, we get x, and then we have to do that on this side. And 30 divided by 2 is 15. So we would need to add 15 ml to the IV bag for this one. Subcutaneous injections are administered in the subcutaneous or fat layer of the skin. Most subcutaneous doses are less than 1 ml. For intramuscular injections, the needle passes through the cutaneous and subcutaneous layers of the skin, and the injection is delivered into the muscle. Small volume IM injections are less than 3 ml, and a large volume IM injections are 3 to 5 ml. Larger muscles can handle the larger amounts, but 5 ml is the volume limit on IM calculation or IM injections. Therefore, if you calculate an IM dose and your answer is greater than 5 ml, there's probably an error either in the prescribed amount or in your calculations. Hospital pharmacy techs prepare and deliver a 24-hour supply of IV solution to nurses' stations daily. Large volume parenterals contain more than 250 ml of solution, and small volume parenterals contain 100 ml or less. Most intravenous piggybacks are SVPs, which are small volume parenterals that are given over 30 to 60 minutes. LVPs for continuous IV administration are hung at the patient's bedside and are allowed to drip slowly into a vein either by gravity or through a pump. They must be given at a slow rate because veins can only handle a small volume over a given time. Both large and small volume parenterals must be infused at a constant rate. In either case, the physician determines the infusion or flow rate in terms of milliliter per minute, drops per minute, or amount of drug per hour. The pharmacy technician must be able to calculate the volume needed to last a certain amount of time to calculate how much longer a currently hanging IV solution will last. Depending on the order received, the technician must be able to convert the numbers to determine this information. This ultimately determines the amount of IV solution to be prepared for a 24-hour period. So here is just a depiction of a large volume intravenous drip with smaller piggyback attached to tubing on the pump. A rate is defined as something per unit of time. An infusion rate or flow rate refers to the amount of IV fluid entering the body over a specific amount of time. We'll go through some examples of that now. So now we're going to go over intravenous infusion flow rates. They're the same thing. You'll hear it called infusion rate, flow rate, and even administration rate at some point. Again, just a little refresher from what I just said. An infusion rate or flow rate refers to the amount of IV fluid entering the body over a specific amount of time. So we do have a formula for that. So a flow rate is equal to volume over time. So volume is going to be, should be in milliliters. And the time can be minutes or hours. All right, so let's look at that first example. So a 1000 ml IV may be ordered to run over 8 hours. The infusion rate would be 1000 milliliters over 8 hours, so that's volume over time, which reduces to 125 milliliters per hour. That's lowest terms. And a 1000 ml may be ordered to run at 50 ml per hour. So we already have the flow or infusion rate here. And we want to, and this one they set up like a proportion, so we can look at this one. So they have 50 ml per hour. That is the run time. That is the infusion rate. So whenever you see milliliters over time, you should know that that is either the infusion, flow rate, or administration rate. So if we ran a 1000 ml IV for 50 ml per hour, that would take 20 hours because we would do a 50x and we'd set it up as 1000 times 1. And let's just do it just so you guys can see. So 50x is equal to 1000 times 1. So 1000 times 1 is 1000. And we want to get x alone, so we're going to divide both sides by 50. Now we have x, and then of course we have to divide that by 50, which would give us 20 hours. And I didn't set up the proportion, I just did the math, but this is exactly how the proportion would be set up. So the next example, we have heparin 100 units per 500 ml to run at 10 ml per hour. How many units will be delivered per hour? And you can see that up here, they have the basic necessary conversion factors. So you will be using 1 hour equals 60 minutes and 24-hour equals 1 day. So for this one, we have 100 units per ml. A drip rate, sometimes called drop rate, represents the numbers of drops administered over a specific time via intravenous infusion. It is a specific type of infusion or flow rate, usually measured in drops per minute. Calculations are affected by the size of the tubing used to deliver the medication. A drop factor is found on the tubing package. Various drop factors are available. 10, 15, and 20 drops per ml are all called macro drip, and 60 drops per ml is considered a micro drip. Right, we'll do some examples of these now. Okay, so the next type of hospital type IV calculations are drip rates. They're sometimes called drop rates. They represent the number of drops administered over a specific time via intravenous infusion. So for these, we have a formula as well. It's volume over time times the drop factor. So the drop factor has to be given to you for you to be able to do this problem. And I don't think they have you ever calculate it. And then the volume, of course, is going to be milliliters still, but for this one time, it should be in minutes. Because our answer at the end of this math problem should be drops per minute. So let's see, first example here. So you receive an order for a 2-liter bag to be given over 24 hours. The tubing delivers 15 drops per ml. So that is the drip or the drop factor, sorry. That is the drop factor, 15 drops per ml. What are the drops per minute? So our volume is 2 liters and our time is 24 hours. But remember, here we have to have it in milliliters and minutes. So for the volume, it is a 2-liter bag. So remember that 1 ml is equal to 1,000 ml. Or I'm sorry. In the practice of pharmacy, percentage can be expressed in 3 ways: weight per volume, and volume per volume. Weight to weight is percentage is the number of grams of solute dissolved in 100 grams of final product. Weight and volume percentage is the number of grams of solute dissolved in 100 ml of solution. Volume is the number of milliliters of solute dissolved in 100 ml of solution. Okay, we'll do some examples of those right now. All right, so let's look at this example here. You receive an order for a 2-liter bag to be given over 24 hours. The tubing delivers 15 drops per ml. What are the drops per minute? To find this out, prepare the problem. So identify the drop factor. So this tubing delivers 15 drops per ml is the drop factor. Your drop factor should always be in drops per ml. And what are the drops per minute? And to find this out, prepare the problem, just like we said. So how many milliliters will be delivered per hour? So if 1 liter is equal to 2,000 ml, which they have here, or sorry, if 1 liter is equal to 1,000 ml, then 2 liters has to be 2,000, and it's going to be over 24 hours. But we should figure out the time in minutes. So if we have 24 hours, and we times that by 60 to get minutes. 60 minutes are in an hour. We get that there is 1,440 minutes in 24 hours. So our volume, of course, was the 2,000 ml because 1 liter equals 1,000 ml. So 2 liters equals 2,000 ml. Our time is 1,440 minutes. Equal sign. I did not want to. And then we're going to times that by the drop factor. Remember, was 15 drops per ml. So we can first cross off like units. So we have 2 milliliters, so those are gonna be gone, not the number, just the units. So now you can see we only have the units of drops per minute, which is what we want in our answer. So now I'm just gonna get out my calculator and I'm gonna do 2,000 divided by 1440 times 15, which gives me 20.8. Which down here you can see is what they got as well. They did some other steps that I don't think were necessary to do that. As long as you can, like here, they did the 2,000 over 24 and then got that. You don't need to do that if you can just convert your milliliters and your time. It's much simpler. Okay, so now we're gonna do the ratio in percentage example, so the percentage and ratio strengths. So just a little review from what I just said. In the pharmacy, we use percentages in 3 ways: weight over weight, so grams over 100 grams, weight over volume, grams over 100 ml, and volume over volume, milliliters over 100 ml. So you can see that all 3 of those are out of the bottom number is 100 because percentages cannot be more than 100. So if you can just remember that part, this will be a little bit easier. A lot of students get confused by this and really we shouldn't. So this problem, how many grams of dextrose are in 250 ml of 10% dextrose solution? So we are going to do a proportion. Now, looking at the 3 different ways. In this problem, we have milliliters and grams. So that right there tells me that I'm going to probably have a problem that is going to be weight volume, sorry. So then I'm going to take my percentage. So let me go to my thing here. So we have 10%. So 10%, and that is like the grams per milliliter. So 10% is 10 grams over 100 ml. Now, if that's confusing, I just took the 10% from here, and remember that's out of 100, but this is also using the rule of grams over 100 ml. So we have 10 grams over 100 ml. So that's going to go on one side of our proportion. And most of the IV bag fluids are going to be in percentages, so these are really what you're going to be calculating for the most part. And if we look at the order, they want 250 ml and they want to know how many grams. So 250 ml will go down here because we want our units to be directly across, and our X grams will go there. So for this one, we would do 100X is equal to 10 times 250. So 10 times 250 is 2,500. And we want to get X alone, so we need to divide this side by 100 to get X alone, and then we also need to divide this side by 100. So this gives us the answer of 25 grams. So there are 25 grams in 250 ml of 10% dextrose. And then the next example, what is the percentage strength of an ointment containing a 0.5 gram of active ingredient in 50 grams? The pharmacy often receives a prescription for a liquid or solid medication that is not available commercially in the strength prescribed by the physician. Often the commercial strength is greater than the prescribed strength. In this situation, the pharmacist or pharmacy technician must dilute the commercially available product to a lower strength. In this process, called dilution, a pharmaceutical preparation is diluted through the addition of a diluent or solvent to reach the desired strength. The diluent is an inert substance that does not have a concentration. In other words, it has a concentration of 0%. The diluent adds either volume or mass to the preparation. Sterile water is a common diluent for solutions, and petroleum is a common diluent for solids. Liquid dilutions involve adding a diluent like sterile water with 0% active ingredient to a higher concentration stock solution. During the dilution process, begin with the stock volume of a particular percentage concentration. Add a diluent to the stock solution to achieve the desired volume and desired percentage strengths. The strengths must always be expressed as a percentage, and the volumes must be in the same unit. Usually the volume is requested in milliliters, but occasionally a physician may request liters or ounces. The process can be expressed mathematically as SV times SP equals DV times DP. 3 of the 4 variables are needed to perform this calculation. The amount of diluent needed can be calculated by using the following equation. So the amount of diluent needed is equal to DV minus SV. The process is the same when diluting weights. Adding a product such as petroleum to a stock solid dilutes the preparation to a lower strength because petroleum has 0% active ingredient. Just change the formulas to read this way. So SW times SP equals DW times DP, and amount of diluent is equal to DW minus SW. So for those of you that were in the math mod previously or taken it before, you might remember these. They have in the math book, though, they use, instead of SP and DP, they use SS and DS for stock strength and desired strength. It's the same thing. Don't let that throw you off. All right, now we'll do some examples of those. Okay, so some dilution examples. We have this formula again, SV times SP equals DV times DP. SV stock volume, SP stock percent, DV desired volume, DP desired percent. So again, those of you that have been in the math mod, you might remember that that book uses, instead of SP and DP, it uses SW and DW for stock weight and stock or desired weight. So let's just jump right into the first problem. So first, what I always recommend is that you write the formula out on your paper. So SV times SP equals DV times DP. And then over here to the side, write all of those out in a row. So we can easily identify our variables and then just plug them into this formula equation. So how many milliliters of water must be added to 150 ml of a 25% weight volume stock solution of sodium chloride to prepare a 0.9% weight volume sodium chloride solution? So always when you're looking for your desired, you're going to look for prepare, right? Make. What the doctor orders or an order contains or physician orders. So our desired percent is going to be 0.9%. So I'll write that here. And I don't need the percentages or any of the units for the problem at the moment. Oops, sorry, that's desired, not. 0.9. All right, and then we have in stock 150 ml of a 25% solution. So the 25% is our stock strength, and our stock volume was 150 ml. Our desired volume, we don't know. That is what we're looking for. So our SB is 150. Oops. We again don't need to put the units there. I'm so used to doing it. Because it can throw you off a little bit. So 150 times 25, that little means 25, is equal to dV, which we don't know. So I'm going to leave that as dV, and then 0.9 for dP. So just like in the other problems, we want to take care of the multiplication on the side that has two numbers. So 150 times 25 is 3,750. And then I'm just going to rewrite the rest of the problem out. So just like in those problems, this time we want to get dV alone. So to do that, we need to divide the side by 0.9, and then we get dV, which is what we want. But of course, we need to divide this side by 0.9 as well. So 3,750 divided by 0.9, which gives us 4,167 ml or 0.67 ml. Let's see what they have. It's 4,167 ml. So that is our desired volume. Now, the next step is to do the amount of water needed. So that's going to be dV minus SV. So the dV is what we just figured out, 4,167 ml. And oops, that's it. Sorry, guys. So dV minus SV, and our SV is 150 m. And that will tell us how much water we need. So 4,167 minus 150 gives us 4,017 ml. Alligation alternate is a method used to calculate the number of parts of two different strengths of medication needed to prepare a third strength that is not in stock. For example, if a physician orders 20% potassium chloride and you only have 10 and 50% in stock, you can calculate the amount of each solution needed to attain a 20% solution. You can achieve this only when the strength desired is between the two strengths being mixed. This means that you cannot make a 20% solution from a 5% and a 10% solution. However, you can make a 20% solution from a 5% and 70% solution. The alligation process is the same when dealing with weight or volume. If a 0% diluent is used, such as water for volume or petroleum for weight, you can use the alligation method or the equation from the dilution section. All right, so now we'll go over some examples of those. Okay, so alligation alternate example. So again, just a little review from what I just said. A method that is used to calculate the number of parts of two different strengths of medication needed to prepare a third strength that is not in stock. And just a little note, you can achieve this only when the strength desired is between the two strengths being mixed. Me. So in stock are a 70% solution and a 20% solution. How much of each are needed to create 1 liter of a 40% solution? So a good indication that you're going to be doing an alligation versus a dilution problem is there is going to be 3 percentages in your problem. whereas the other one might only have 1 or 2 at the very most. So our first step is to draw a tic-tac-toe board. Okay. Place your desired strength in the middle, which was 40. We're going to put our higher strength in the top left square and our lower strength in the bottom left square. So 70, was that 20? All right. Then we're going to fill out these two corners. So we're going to do the difference between 70 and 40. So 70 minus 40 is 30, and that will go here. So I'm just kind of going directly across. And then this one, 40 minus 20 is 20. So that's going to go here. And then now I'm going to add these two numbers together, 20 plus 30, which is 50. And then I'm going to write a fraction bar next to them. And on the bottom, my 50 is going to be there. Now for my numerator, I'm just going to carry over my numbers. So this would be 20 and this would be 30. No need to reduce these two lowest terms. It doesn't matter. We're going to get the same answer. So there's really no point of doing it. Now we need to multiply both of these fractions by the amount that we're making. So 1000 ml, because that's 1 liter. So you can see that's something you're going to need to remember. So 1000 ml. All right, so now we can do our math. So the first one is going to be 20 divided by 50 times 1000, which gives me 400 ml. The second one is 30 divided by 50 times 1000, which gives me 600 ml. So these are nice because you can kind of check your answer. Your two numbers should add up to what you're making, and it does. So we can read it across. This is for the 70%. So we need to add 400 ml of the 70% solution, and 20% solution, we need to add 600 ml, and that will make our 40% solution. Percentages are used in the pharmacy to identify the strength or concentration of a medication, to perform dilution problems, and to calculate the markup, discounts, net profits, and gross profits in retail pharmacy. Both the Pharmacy Technician Certification Board examination and the examination for the certification of pharmacy technicians contains math problems using percentages. The easiest method to use for finding percentages of quantities is ratio and proportion, because percentage is an amount per 100. Each of the following 3 questions asks something different, but all can be answered by setting up a ratio and a proportion. So we will work out this problem now together. Okay, so some business math examples. So percentages of quantities, example. So the easiest method for finding percentages of quantities is, of course, ratio and proportion, because percentages is out of 100. So what is 50% of 15? So you can see in this problem, they have it as a proportion. There's no units for this, so don't let that confuse you. So our 50% is going to be 50 out of 100, because we know that, because percentages out of 100. And we want to know what is 50% of 15. So 15 is going to be on the bottom. And then we will solve for X up here. So right, 50 out of 100 is equal to X over 15. So then we would do 100X, because remember, we're going directly across, is equal to 50 times 15. 50 times 15 is 750. We want to get X alone, so we're going to divide this by 100. And now we have to do the same to the 750 on the other side. So the answer is 7.5. So what is 50% of 15? 7.5. So what we did was method 1, we set up a ratio and proportion, we cross multiplied it and divide. Method 2, when calculating what is X% of problems, it is also easy to change the percentage to a decimal and then multiply. So 50% equals 50 divided by 100. So remember back from the beginning of this video, to change a percent to a decimal, all we need to do is divide by 100. So here they have taken the 50% and divided by 100 and got 0.5, and then they just did 0.5 times 15. So now going down to this example, most problems in retail pharmacy can be solved with method 2. So an invoice from the supplier states that the pharmacy can receive a 1.5% discount if the invoice is paid within 10 days, but the entire amount is due within 30 days. How is the discount determined? The amount due is 500. So we want to find out how much 1.5% is off of 500. So again, they just took 1.5 and divided by 100. Oops. And got 0.015 and then multiplied it by 500 to find out that the discount was 750. And then the total due within 10 days. So they took the 500 and minus the 750 they would save if they paid it within 10 days. And it's 492.50. So another use of percentage is to calculate the markup necessary so the pharmacy can make profit. So the pharmacy purchases medication at wholesale costs, the purchase price, and then marks them up to the retail price, which is of course the selling price, so that they can make a profit. So for the example 6.34, the pharmacy must increase the cost of cold medicines by 56% to make a profit. Determine the markup and then calculate the total retail cost of the product. So it's Tylenol, cough and cold, $5.50 is the wholesale price. And 56% we want to turn into a decimal. So if we do 56 divided by 100, we get 0.56. And then we would multiply that by the 550, the amount that we paid, and that would be that we need to mark the medication up $3.08. So we would just add that on to the 550. And that's 858. All right, so that's it for chapter 6. Please don't let this overwhelm you. If you've already taken the math mod, this is nothing new. This is all review for you. If you are new or haven't taken the math mod yet, this is just going to prepare you for the math mod. The type of math that we're doing in this chapter is literally pretty much all the math we're going to learn throughout the whole entire math mod, which is of course like 5 weeks. So it's not going to get any harder than what it is now. So don't like see these problems and go, oh my gosh, how much harder is it going to get? Because it's not going to get any harder. A lot of these just involve simple math. So try not to look too hard into things, but if you need help, you are able to reach out to your online instructor, either whoever it is. And then you can also reach out if your local campus by you has a lab instructor that works there once a week. You can also go in with them and get in-person tutoring.